Scissors cuts paper. Paper covers rock. Rock crushes lizard. Lizard poisons Spock. Spock smashes scissors. Scissors decapitates lizard. Lizard eats paper. Paper disproves Spock. Spock vaporizes rock. And as it always has, rock crushes scissors.
Welcome to our series of videos examining game theory. One of my favorite classes to teach. And this video is part of a series where we're going through an entire course. So I hope you're enjoying it if you've tuned into some of the earlier ones. If not, and this content interests you, please click like and subscribe and hit the notifications bell. You will then receive updates whenever I post a new video, which will be regularly over the next couple of months. So today we're talking about defining the games within game theory. You know, maybe not the most exciting lesson, but it is pretty important that we all speak with the same vocabulary. So part of the reason for this video and this lesson. So within game theory, first of all, I think it's pretty important to understand that we are studying what are strategic games, not strictly games of chance. So strategic games, a pure game of chance like a slot machine, we're not really studying that. Slot machines, bingos, things like that. So these are games, they are strategic. Usually they are involving multiple players. And of course there has to be some mutual awareness of the cross effects of any decisions that are made. So within a lot of the games, it really only makes sense if the players understand that, okay, the opponent could do something and that affects me, and I could do something and that affects the opponent. If we don't have that, it really doesn't make as much sense. So we put together these games. There's some set of decisions that are made within the games, and that leads to what we call an outcome, right? Kind of common sense that would happen, but there's some outcome. And within an outcome, there's a payoff. So for example, if we're in a football game, an outcome might be that the offense threw a screen pass to the right and the defense blitzed. Okay, well that happens. What's the payoff then? The payoffs would likely be the result of the play. Were there yards gained? Were there yards lost? Was it a touchdown? I mean, what exactly happened? That's the payoff of the particular play. Now, in that case, like the example I just went through, ahead of time, if you have an offense doing a screen pass when the defense is blitzing, there's a range of things that could happen. Maybe some of the time, because of the blitz, the defender, there's so many defenders near the quarterback, one of them raises their hand and bats the ball down. Maybe some of the time, though, the quarterback gets the pass off and all of the defense is beyond the running back, and on the screen pass, it's an enormous gain for the offense. When it's not known with certainty, though, you could come up with what you would call an expected payoff. So if something happens and you think one side is at a better advantage, you could reflect that within, that a particular outcome leads to an expected payoff of whatever it is that you are measuring. Now, we do assume rationality in our games. It's assumed that all players are rational. There are times we're going to relax this assumption throughout the course to assume that maybe it isn't as rational, or, instead of following an irrational strategy, to say somebody makes mistakes. What I would challenge those in the course, who are through the series, or really in life, often when something seems irrational, there's something else going on that really makes it not irrational. And there will be times throughout the course where that's going to happen, where we will come up with a theory and people don't behave according to the theory, but there's some other wrinkles thrown in that really make their behavior pretty understandable. So it's one thing I'll challenge you to be thinking about throughout the course. Now, we do assume the game rules are known when we're modeling here, that all the rules are commonly known by all the players. Once again, this is something you could relax. You could do games where that's not the case. It's extra wrinkles once again. When we're starting off, we're going to start off. It gets tricky enough and we can get enough insight, even with these somewhat strict assumptions, and then we can go ahead and start to relax an assumption here, an assumption there, and see what we come up with. When we're looking at sequential games, contingencies matter, and we have to think through the contingencies when we're modeling the games. And really, the players who are playing the games, they should be thinking through all the contingencies as well. So contingency is an event that may or may not occur. In real life, you often hear of a contingency plan should something happen. So in the event a player adopts a particular strategy, what's the contingency plan? Or here we're going to say contingency strategy. So contingent strategy adopted when it is known that a contingent event has occurred. This contingencies, this is something that really is applicable to sequential games. When we're studying a simultaneous game, it all happens at once. This isn't as relevant. But this is a nice segue into, once again, further definitions. Simultaneous versus sequential games. So, simultaneous, right? Everything happens at once. Or it might not happen at the exact same time, but when the players are all taking the actions, they don't know what the others did. And if that's the case, the effect is the same as if it were just a simultaneous game. In a sequential game, right, there's an action, and then another action, and then another action. Person must consider what an opponent would do in the future. And that type of analysis kind of gives you a guide. You can have games that have both, and we will study some games that have both. Some sequence and then some decisions that are made simultaneously. Time for, you've heard me talk now for a few minutes. Let's get to a pop culture clip that shows this. The Big Bang Theory, I highly recommend you check out Bazinganomics for far more economics within the Big Bang Theory. Let's check out this clip where we're looking at a rock, paper, scissors game where they have their own little wrinkle to it.
How about we go rock, paper, scissors?
Well, I don't think so. No. Anecdotal evidence suggests that in a game of rock, paper, scissors, players familiar with each other will tie 75 to 80% of the time due to the limited number of outcomes. I suggest rock, paper, scissors, lizard, Spock.
What?
It's very simple. Look, scissors cuts paper, paper covers rock. Rock crushes lizard, lizard poisons Spock. Spock smashes scissors, scissors decapitates lizard, lizard eats paper, paper disproves Spock, Spock vaporizes rock, and as it always has, rock crushes scissors.
Okay, I think I got it.
Rock, paper, scissors, lizard, Spock.
So we saw the little, wrinkle, which was rock, paper, scissors, lizard, Spock. Yeah, we're not going to try to plot that out. But we are going to take a moment for this simultaneous game of rock, paper, scissors. How do you write the payoff matrix for this game? What I would recommend, if you are students in my class right now, you're taking the class for credit, and this is the time to pause the video and work it out on your own. I would recommend that for everybody who really wants to kind of think through this before I just give it away what the answer is. It's much better for learning. Go ahead and pause and grab a sheet of paper and plot out what it looks like. What it will look like, first of all, when we're writing out a payoff matrix. Remember, we have to put the players. One player is a row player, one player is a column player. We're just going to call them player A and player B. If you want to name them your Big Bang Theory characters, feel free. And then each player can pick a particular strategy. What are the three possible strategies? It's playing rock, it's playing paper, playing scissors. So to start, right, we've got player A plays the rows, player B plays the columns, and each one could choose rock, paper, and scissors. Within the payoff matrices, remember, player A goes first, player B, in terms of the payoffs, I'm sorry, player A's payoff is listed first, player B's payoff is listed second. And this has it all set up. Now we have 9 cells within the payoff matrix. How do we fill that out? Okay, so how do we fill this out? Well, if they both play the exact same thing, it's a tie, right? So we'll just put tie, tie. So that's when they both play rock. That's going to hold if they both play paper. That's going to hold if they both play scissors, right? That's the outcome here. Well, what happens if player B is playing rock and player A is playing paper? Paper covers rock, so player A wins, and remember player A's payoff. Player A's payoff goes first. Player B loses, so it's win. The player playing paper beats the player playing rock. Which, of course, then maybe it's easiest to go over to where it's rock paper. So we just have the flip side where player A is playing rock and loses because player B covers the rock with paper. There we go. What about scissors and rock? If player A plays scissors, player B plays rock. Player B loses. Player B wins. Oops, and I will just change this to lose and win. If player A plays rock and player B plays scissors, if player A plays rock, player A wins, player B would lose. And the final one, what happens about paper versus scissors? Well, scissors wins. So if player A plays paper, player B plays scissors, then we see that player A loses, player B wins. And the opposite will be in this cell. And now we've completed out the payoff matrix, right? We've got the players. We've got the row decisions for player A, the column decisions for player B, and then for each of the possible outcomes, there are 9 possible outcomes in this game, we have the payoffs associated with those outcomes. So you see how the definitions kind of lend themselves naturally, right? We're doing that. It all kind of seems natural once we know the language. So two different ways we can present games. We touched on this in the earlier video a little bit, but there's normal form or extensive form. Normal form takes the form of a payoff matrix, which we've worked with so far. Extensive form takes the form of a tree diagram. So far, we're working with payoff matrices. We will be looking at tree diagrams, though, very soon. So what we just saw was a payoff matrix. Now, we could put rock, paper, scissors quite easily into a tree diagram. As a general rule, it's not always the case, but as a general rule, when you have a simultaneous game, normal form's often easier. When you have a sequential game, a tree diagram is often easier. Okay, what else to consider here? Key consideration, are the players' interests in total conflict, or is there some commonality? Some games are completely a zero-sum game, right? If you're playing poker, right? For each win, there's an equivalent loss. Actually, if you're playing poker at a casino, the casino takes a small portion, so it's actually less than zero sum overall, but I think many people would say that's kind of the fee for the entertainment. But, sporting contests, right? If you've got a penalty kick, the kick goes in or it doesn't, right? This is a zero-sum game. But most games, quote unquote, that we study aren't zero-sum. So economic trade, right? That's not a zero-sum game because there's gains from trade from both sides. Now, how much does each side gain, right? That's where the game theory could work in. Wars, definitely not zero-sum, and avoiding wars is positive. Going into wars is negative-sum. Plenty of other examples we'll come up with that it's not a zero-sum game, right? That it's, and the best types of games are when you can find something that is positive. Each side can end up gaining. What we will end up studying, a lot of the games are going to have some tension between cooperating and conflict. Other things to think about as we go through the course, is the game played one time only, or is it played a repeated number of times? We're going to start with one-off or one-shot games, as they're often called. We will be going through repeated games later. They add some interesting and fun wrinkles to things when a game is repeated multiple times. Are the rules of the game fixed or not? We're going to assume fixed. It changes things dramatically if the rules of the game are not fixed in incredible ways. has major implications, and it's really had major implications within economics way beyond game theory, to think about what happens if, say, the government changes the rules of the game and how does that impact things. But we are going to assume the rules are fixed within the games. Do the players have full information or equal information? This is discussed in a great deal kind of as we move through the course. Often we assume, there's full information, but you don't always have full information on what actions were taken, and it leads to some interesting issues where we have what are called information sets. We know one of some set of actions are taken, but we don't know the exact action that was taken. Really can be interesting and important for us to study those. And are agreements to cooperate enforceable? Generally, we assume they are not. So that you could say you're going to cooperate, like in the previous videos, one of the previous videos we showed the example from Golden Balls. You could say you're going to cooperate, but the agreements aren't binding on cooperation. That is all for this video. It's part of the course on game theory. Hope you enjoyed it. Once again, if you did, there will be plenty more coming, so I look forward to seeing you in the next video.